Okay, well, while Paul is setting up, let me just introduce him. He, as you probably all know, anyone who's here is a early universe cosmologist who's worked on inflation, but also bouncing universe models, which we'll tell us about today. I guess I'll also say, by way of introduction, that he has sort of a separate life doing condensed matter physics providing sort of the original description of theoretical description of quasicrystals, but then that's an ongoing thing where I think more recently they've discovered the first naturally occurring quasicrystal. And in any case, I will say that on the Perimeter website there are occasional popular talks a few times a year given by visitors to audiences in Waterloo. And Paul, there's one on the web at the website persa.org. It's where all the Perimeter talks are cataloged. And he gave this great popular introduction to quasicrystals for anyone who's interested to hear about it, but not ready to read a textbook about it. I really recommend it. Anyway, welcome, Paul.
Thanks, David. Well, it's a great pleasure to be back here at CITA after too long an absence. I should first of all apologize. This is a talk I was supposed to give last January, and then 2 days before I discovered that stupidly I had lost my passport, so it took me a few months to recover from that. So I apologize for the lateness of this talk. I also want to say publicly for the people here from CITA that, well, of course, CITA has been really important to me and my students and postdocs over many, many years. And so, other than the little fiasco last January, what I really regret is over the recent past not being able to come to two really important events. One was the remembrance for Lev, a dear colleague, a wonderful scientist, and a great leader, as you all know. And the other was the celebration of the day. Unfortunately, both those events conflicted with family events. There were major family events. I just couldn't figure out how to be in two places at the same time. But my thoughts were very much with you, and well, I'm glad I could come back today and say that and tell you a little bit about some of the things that we've been working on. So, in the standard model, standard Big Bang inflationary model, one presumes, without proof, that the universe began with a Big Bang. That was the beginning of space and time. The universe began from some sort of quantum event that could have produced anything. Perhaps, maybe more likely, some sort of chaotic disordered state. And then we know observationally that within a second it was in a very special state, a very homogeneous and flat state. And so in order to explain how we got from one moment to the other, we need some sort of mechanism which is very powerful and operates very rapidly. And that in a nutshell is the argument for inflation. Inflation is the one scheme we know of which is powerful enough and rapid enough to do a trick. And to a large degree, that little story I just told you is the argument that I think that most of us walk around with in our heads, that we learned at some point in the past, and we walk around with our heads, and that convinces most people that inflation is a very powerful and perhaps the right model of the universe, even though that's not yet proven, even though there are, as we'll discuss, there are some problems with that picture. So what I want to talk about today, though, is an alternative possibility, which is based on the idea that the Big Bang is not a beginning, but some kind of bounce, some kind of transition from a pre into a hot expanding phase. And this is an idea that's been developing for the last decade or so, several different versions of this idea. And I think now is a good time to present a kind of overview of this picture of what we've learned, what we've distilled from it. Because well, it's a little bit like the story of inflation. For those of you that were back there in the 1980s, and there were a few people, not too many, were back at that time. If you were back there at that time, you might recall there were a number of confusions and misstatements about inflation at that time, which kind of got boiled away after a few years, and the simple story that the rest of you have learned has emerged. Well, the same has happened here, where there's been a number of confusions and misunderstandings that have now been straightened out. And now it's, I think, worth giving an overview of this story to present the point that there is, in this case too, also a sort of forceful and compelling story to tell. That's not to say that the picture is complete, that there aren't holes, that there aren't open issues. But I would say that we've now evolved to the point where the open issues in this picture are actually pretty much one-to-one corresponding with open issues that exist in the inflationary scenario as well. And there may, as I'll try to explain, it may even be some advantages of this picture relative to inflation. So it's an interesting alternative to consider at this time. So basically what I'm going to try to do is first of all tell you why the bouncing models are interesting in the sense that they can offer alternative ways of solving the famous cosmological problems or explain the large-scale structure of the universe. Then I'm going to talk about how you can test them, how you might be able to rule them out with data that we have in hand. And then the subject which I guess I've been moving more and more towards in the last few years has been what are the advantages that these models might have over inflation. The one thing I won't say too much about, unless I have more time than I expect, will be the bounce itself. The bounce is the key open issue for these cosmologies. Just like in the Big Bang inflationary picture, the key open issue is what actually happened at the Big Bang and how we end up having to get into inflation. There are a number of ideas about the bounce that people are exploring. Some based on quantum gravity. Those models based on quantum gravity are often referred to as singular cosmologies. And these cosmologies, classically, the scale factor really gets very, very close to zero, which is zero itself, and to the point where quantum gravity corrections become important. Examples of these are ideas built on string theory, or loop quantum gravity, or other alternative ideas. And then there's also bounces which are based on non-singular cosmologies, where the scale factor bounces at a finite value of the scale factor when classical gravity is still perfectly valid, well before quantum gravity effects become important. And so there's bounce models of that type as well. What's important for the purposes of this discussion is that all those bounces share the common feature that they involve bounces which end up being analytic and unitary. So that the way the universe evolves leading up to those bounces carries forward in a continuous way to afterwards, and that's all I'm going to need for the purposes of my discussion. So there are a few minutes at the end, I'll tell you a little bit of news about bounces themselves, but otherwise I'm just going to presume that that the bounce solved by one of these solved by one of these ideas. Okay, so why are the models interesting? Well, I'm interested in bouncing models generally, but just for the sake of concreteness, I'm going to be talking about a particular example of one based on the cyclic universe. This is a model in which the bounce is a transition from a big crunch to a big bang. And in the cyclic model, actually, the universe goes through a sequence of evolution that keeps repeating over and over again. So the bounce doesn't occur once, but it occurs repeatedly. For the purposes of this discussion today, I'm not going to worry about the cyclicity of it. That's a special case of that particular model. I'm just interested in the question, what happened at the Big Bang? What happened 14 billion years ago? Was it a bounce, or was it a beginning? And was the large-scale structure of the universe set up by events that occurred after the bang, like inflation, or before the bang, like in the alternatives we'll talk about here? I'm only really interested in one bounce. But just to outline the story, this is a model in which the universe goes to a bang to radiation domination without stopping with any inflation. The homogeneity and isotropy is what it was set up. Matter domination, dark energy. Then one goes to a phase of contraction, which is the phase we're most interested in, and then a crunch back to the Big Bang again. As I said, the important thing about this model is that the Big Bang is a bounce, and that preceding that bounce is a phase of contraction, and more specifically, an eonotic type of contraction. Okay, the first thing I want to point out is that the moment that you begin with the idea that the Big Bang is a bounce, and then it's preceded by a phase of contraction, you immediately resolve two of the famous problems that plague Big Bang cosmology that inflation is designed to solve. First is the causal aspect of the horizon problem, and the second is the flatness problem. So the causal aspect of the horizon problem is the fact that we observe regions of the universe that seem to be remarkably similar today, which in the non-inflationary Big Bang model extrapolated back to the Big Bang, were never in causal contact before. That's based entirely on the idea that the Big Bang is the beginning. If there was evolution that occurred before the bang, you have arbitrarily large amounts of time for those parts of the universe to be in causal contact. There is no causal bound. So that means you can begin to think about smoothing processes that don't have to be as rapid as inflation, don't have to take 10 to the minus 30 seconds. In fact, the kind of smoothing processes we'll be talking about take more on the scale of 10 billion years. They're slow processes, not rapid processes. But you have plenty of time if the Big Bang is not the beginning. So the causality aspect, the causal connectedness immediately is not a problem. What about the flatness problem? Well, what is the flatness problem? The flatness problem is if you have a universe which begins with, let's say, a small amount of curvature shortly after the bang, and if the universe is decelerating, so it's slowly expanding, and you follow forward in time, the curvature becomes more and more important in the Hubble expansion, in its contribution to the Hubble expansion. So that today, 14 billion years later, it's quite shocking in that picture that the curvature is totally dominating the universe. Now, what that means is that the universe is unstable in the sense that going forward and during expansion it becomes more and more curved. Now just run that picture backward. If you have a universe which is contracting and begins with a significant curvature and you just run it backwards, it just becomes flatter and flatter. So flatness is not a problem in a universe that's contracting. As it contracts, the flatness, the curvature becomes less and less important. It's homogeneous and isotropic. And so all you need to solve the flatness problem is to make sure you have more of a contraction effect before the bounce than after the bounce. So what I'm trying to do is sort of break down certain conceptions we commonly have that inflation, for example, is the only way to solve the flatness problem. No, here's another possibility, another logical possibility. Now, it's not enough to do the trick.
Well, what about initial inhomogeneities? Wouldn't those tend to...
We'll talk, yeah, so good. So we'll talk, this is not enough to solve all problems. It's not enough to solve the homogeneity problem in the general sense. We have to do something more special than that. We have to do something, not just make it contraction, but we have to make it an equinotic contraction, in which the ratio of the pressure, the density is greater than 1. Because although the flatness isn't the problem, what actually turns out to be the problem isn't even so much the inhomogeneity, well, not directly, but actually the anisotropy. So what for an expanded universe is the problem of flatness turns into a contracting universe with a problem of anisotropy. So first of all, let's just remind you of the story for inflation. So inflation, if we assume there's been enough inflation that the universe is nearly homogeneous and isotropic, and that we can approximate it well by the Hubble equation, by the Friedmann equation. Then what we imagine is the universe begins with some mixture of matter and radiation that pre-existed before inflation. It begins with some isotropy, which goes as 1 upon a to the 6, some curvature, which goes as 1 upon a squared. And if that's all we have in theory, and then the universe expands, we have the problem that all these terms decrease at different rates, but the term that decreases the most slowly is the curvature term. And that's why the curvature becomes more and more important in an expanding universe. In order to combat this problem, we introduce the inflaton, which acts like a cosmological constant. And the key thing about the inflaton is that it decreases, it's nearly constant, much more slowly than even the curvature. So, letting the universe expand with time, all these terms drop away, including the anisotropy and the curvature, and become totally dominated by the inflaton density. And then when it decays, everything we see is born from this piece, and all these pieces have been exponentially suppressed. So that's the logic behind inflation. Now, if you now run this backwards and have the universe contracting, you can see that actually the inflaton doesn't do no good at all, because now all these terms are growing, and this is the one term that's not growing. So actually it loses to everything. Curvature loses. The one that wins is going to be the anisotropy. So the thing you have to worry about, the contracting universe, is the anisotropy. In fact, it's worse than I've made out, because here I've assumed that I can use the Friedmann equation. I should really be solving the full Einstein equations. And then I discover a worse problem, which is once the anisotropy really begins to take off. If I have any off-diagonal terms in the stress energy tensor or the curvature tensor, I'll begin to amplify those, and the universe undergoes a series of chaotic mixed master oscillations. So as it contracts, actually different regions of the universe see different kinds of anisotropic expansion. Two observers which are arbitrarily, no matter how close they are together to one another, over time we'll begin to see different kinds of anisotropic contraction around them, so that in some sense, at the bang, at the crunch I should say, the universe is maximally inhomogeneous, and the two observers see different things. Yes?
The kinetic energy of scalar fields also goes like 1/8 of the 6, right?
If it's a perfectly massless scalar field, yeah. So that competes in the same level as anisotropy. Great energies would go as lower powers of A. Yeah. So, the idea of the ecprotic contraction is to introduce an energy component which has W greater than 1. This is sort of the analog of what we did with the inflaton. Because during contraction, well, in general, a component with equation of state W goes like A to the power 3, 1 plus W. And what's special about W equals 1 is that the greater than 1 is if W is greater than 1, then this beats everybody. So instead of the universe becoming anisotropic, in fact, just like in inflation, all these terms go away, and the only thing that's going to be left as you approach the crunch is going to be this energy density, this contribution of the energy density. So that conceptually is the idea. So that beats everything. That beats gradients, inhomogeneities, you name it. Now, you might not believe this argument based on the argument what I've shown you here, because I began with a nearly homogeneous and isotropic universe in the first place. You might want to imagine an initial condition which is much more inhomogeneous and ask what happens. And in fact, we've run that exercise working with Franz Pretorius and David Garfinkel using the numerical general relativity codes to begin with rather wild, nonlinear initial conditions, but with an ingredient to the energy density with W greater than 1. And what you discover is that this is a very powerful homogenizer and isotropy of the universe. There are tiny regions of the universe in which you might form black holes, but essentially all the volume of the universe consists of a homogeneous isotropic inside the universe. So, in fact, in some ways, I guess you could even say it's numerically more powerful in inflation in the following sense. In inflation, you have a term which is nearly constant, competing with an A-squared term, so there's only 2 powers of A involved, difference between them here. And here, typical W's might be of order 100 or so. So there's like many more powers of difference in the factor of A here. So inflation is good enough for the trick, but I'm just saying numerically this is a very powerful homogenizing isotropic. So just in this little argument, there are 3 pieces of lore that I think should go out the window. Just remember forever, they're not true, okay? The first is the statement that inflation is the only means of flattening and making the universe homogeneous and isotropic. This is certainly a way that accomplishes the same thing using different physics. The second is that there's also been a common piece of lore that a contracting universe inevitably undergoes chaotic mixed master behavior. Those theorems, which go back to the 1950s, always presume that W is less than or equal to 1. Okay, they fail entirely when W. They're completely untrue when W is greater than or equal to 1. And the other claim, which is more recent when these ideas were first introduced, was that these kinds of models require special initial conditions. And what I just argued for you is that, in fact, the conditions can be quite wild. In fact, that's what we were simulating with Franz and David. And still, this is a powerful enough mechanism to do the trick. Yeah?
Good, but how do you argue that physically W greater than 1 shouldn't even be possible?
Good question. Well, that's the next question I was going to answer. In fact, we have to do more than that. We not only have to get W greater than 1, but well, at least within the cyclic model, we need to fit it within some context in which W is changing with time, and do it in some way which doesn't look completely bizarre and implausible. Because in fact, what we want to do with the cyclic model is more complicated. We want to have a phase of W here 2/3, and W is 0, then -1, because we want to explain the present dark energy. Then we want to have this ecprotic phase where W is greater than 1 by contracting. Here it's expanding, here it's contracting. Then we want to head to the crunch, and it turns out, at least for models, this particular kind of model, this kind of balance, we want that W close to +1, and then we want to be able to go back again. So it's a lot of tricks we're trying to accomplish. But what's interesting is that you can accomplish this trick with remarkably little effort. In fact, with very much the same kind of effort you apply in designing an inflationary model, a scalar field going down a potential. So this represents a schematic of a scalar field going around potential, and the potential shape will probably even remind you of a lot of inflation. It has a plateau and a dip. There's a couple other things going on downstream. The difference between this and inflation is that in inflation you would have put the zero down here with a small gap representing the cosmological or the dark energy density observed today. Whereas here, the zero of energy is over here, where this represents the small cosmological constant. So in inflation, we sit over here today, at the bottom of this dip. In this model, we sit over here on the plateau. Okay, so that part's conceptually different. Now, in both inflation, or in general, if I have a scalar field with a canonical kinetic energy density, it's easy to show that that it contributes a pressure and density, which go like the pressure, the difference between kinetic and potential, and over the energy density, the sum of kinetic and potential. So, for example, you might imagine after the bang, the field being here, and the universe full of hot matter and radiation. What's going to happen, as long as that matter and radiation density is much larger than this positive energy density, nothing happens at all to this field. It's just stuck there by the fact that the Hubble constant is large and produces a large Hubble drag that prevents the field from moving. So the universe will have a ordinary phase of radiation domination and matter domination, and things will only begin to happen at the point that the matter density becomes comparable to this small vacuum density, the small potential energy density. At that point, two things will happen. Number one, this contribution to the energy density comes to dominate, and it acts as long as it's a flat enough potential. It acts like a contribution where W is very close to -1. So that gives you the dark energy that you're trying to explain. And number two, now that the field is no longer pinned by the Hubble friction due to the matter radiation, it's now going to begin to slowly drift. It's not going to stay there forever. You just wait long enough and it's going to make its way downhill. So that's the thing, follow what it's going to do. Now notice that as it's going down the hill, W has to be changing. As it's moving down the hill, for example, here it's expanding with W equals -1. By the time it gets to the crossing 0, V is equal to 0, so now W is equal to 1. So it's already gone from -1 to +1. Okay, still expanding, but you've already gone from acceleration to deceleration just by having it go down to this point. And now you just let it continue to roll. As it continues to roll, the potential energy density becomes negative. The kinetic energy density is still being redshifted because the universe is still expanding. So if you look at this denominator over here, this is becoming negative, this is decreasing. There's going to eventually be a crossing point where that's equal to 0, where the energy density in the scalar field is momentarily equal to 0. That's the point that H is equal to 0 and you have a bounce. The universe bounces. Nothing terrible happens there. W formally diverges, but W is not a measurable quantity. Nothing bad about W diverging. Just follow the equations of motion straight through. And now the universe is contracting. As happens if H is the sign, the universe is contracting. But you still have the potential energy is negative, so now the denominator is always smaller than the numerator. So you're now in a condition where you're contracting with W bigger than 1. So actually you've accomplished two things for the same trick of just rolling the field down the hill. One, you reverse the universe from all the accelerated expansion to contraction. And number two, you've got your condition W greater than 1, all at the same price. Now, if the potential goes down forever at a steep rate, okay, W will remain positive all the way as phi goes to infinity. If, however, that would mean the energy density becomes arbitrarily negative. So it has to bottom out, and it can either bottom out by forming a plateau, or in this example it comes up. It really makes no difference to the scenario. The moment that the potential stops decreasing at a steep rate, the kinetic energy takes over, potential no longer decreases so rapidly, and W approaches +1, which was the last condition we wanted. So this is the example I've given here is the case of what we call the singular bounce, where the bounce occurs as the field goes all the way to infinity and W is equal to 1. That turns out to produce a very special geometry which is conformal and which we think, or nearly conformal, and which we think is, for various arguments, is a good candidate for an analytic unitary bounce. If it's There are models in which instead the potential rises steeply here. Those would be cases that one would design if one wanted to have a so-called non-singular bounce, where the field is going to be brought to a halt, and the contraction is going to be brought to a halt at some finite value of the field and the scale factor. So again, I didn't want to say too much about bounces. I'm going to try to, you can ask me afterwards, or we'll see how far we get, but that's all I wanted to say about that part for the moment. Are there any questions?
Sorry.
Yeah, so.
This one that kind of uses like the previous one. You, in that one, when you run this calculation, at some, so you add this potential, and you start with some random initial condition, and some where the field,
Yeah, so for the simulation, we just started in eonotic phase. We didn't assume this dark energy phase. We just assumed that it was, let's say, potential was forever negative. We just wanted to study just this contraction phase, what its effect would be. So we began with very nonlinear initial conditions and just let it go to see if it could either self-smooth or if it was just totally collapse.
That you once started that one.
And that was much larger than 1. I think it was like 5 or something. It wasn't that big. It was bigger than 1.
It wasn't attractive.
It was attractive. Yeah, well, I'm not sure. I think the correct traction has different meaning associated with it. At the end of the day, the universe was homogeneous and isotropic and flat almost everywhere, except for so-called spiky regions, really widely deformed black holes. But they would be exponentially far separated from one another. So the nonlinearity leaves some memory in the form of these very distantly separated black holes, but basically we produce exponentially large volumes of homogeneous and flat universe. Okay?
So if you carry gratify squared in this, do you show that relative to the homogeneous part becomes negligible?
Yeah, that's for example. I mean, that's certainly.
But that isn't that what you were simulating with
Franz and yeah.
Right.
Yeah.
Okay.
But you would expect that because you know it's going to decay at 1/8. The point is, it's very hard to get anything above 8 to the 6.
Yeah.
It's
Sort
a great
of the
energy
LK
not
argument about that it's mostly a time fluctuation, which is the same kind of thing, or is this one much more dominant than that?
Much more down. So in BKL, they were arguing.
That's the 1/8 of the 6th there.
Let's say, so BKL, first of all, showed that W less than 1 always leads to chaotic mixmaster. W precisely equal to 1 is marginal. Depends upon what the ratio of the energy density is in this scalar field compared to the anisotropy. That's assuming that you have a very, idealistic model. You have just a scalar field and anisotropy. The moment you give the field any interactions, it's unstable. It immediately would produce the BKL oscillations. I mean, the mixmaster oscillations. So W equals 1 is sort of a marginal value. Here, you're getting W much greater than 1, so you're way beyond marginal. This is like super convergence. So that's a perfectly free scalar field plus anisotropy is marginal, depending upon what this ratio is. Anything greater than 1 is more super marginal, super convergent. Yeah.
Did I understand correctly that you said this can be made further?
Yeah, so ask me afterwards. I really just, we have enough to cover with just a single bound. I'm really interested in the practical question, what happened 14 billion years ago. But yes, you can actually show there exists in this scenario solutions which would be similar. Yeah, there's more, you have to add more to the story than I've done so far, but that's actually an interesting possibility. Now, motivation for this, some of you know this well, was thinking about heterotic M theory and the idea that what I described as the scalar field and potential also has a manifestation in terms of branes moving back and forth along an extra dimension. So in this little cartoon over here, you're supposed to imagine that these little pieces of period cloth over here are really three-dimensional branes separated by a fourth spatial dimension. This is kind of the structure of heterotic M theory. They are actually supposed to be infinite, but I can't show you infinite ones without knocking out the whole picture, so it's a little piece of them. What corresponds to the scalar field we've been talking about is the modulus field. It describes the distance between the branes. The field running back and forth along the potential means that corresponds to the field having some finite value here when the branes are this separated like this, and the field running to infinity as the two branes collide and then running back again. So the field and the scale factor are, in this picture, kind of singular coordinates in the limit that the two things collide. They're not good coordinates because even though what's happening is two branes colliding in the middle of someplace, it looks like space and time have disappeared in those coordinates. You need to use other coordinates. But for describing the rest of the story, which is the part that we're going to be describing, this is an equivalent picture for many purposes. So what I want to say about this is, on the one hand, it's not essential to the story. I mean, it's the way we were thinking about it in the first place. But the part of the story we're going to be talking about today doesn't require branes or extra dimensions or anything like that. On the other hand, if you like thinking about it from this point of view, if you're comfortable with thinking about this point of view, it's actually very convenient because a lot of the physical processes that occur with the mathematics have a very simple geometric interpretation in terms of this picture. So in particular, the bang is just literally a collision between the branes, where they either bounce off one another or in another set of coordinates pass through one another. Okay, so it's a very simple interpretation in which you can think about analytically continuing through this process. Okay, so that's the homogeneous cosmology. Of course, if you want to have a competitive cosmology, you also have to explain the inhomogeneity in the universe. There, the mechanism that one uses in these scenarios is very analogous to what one does in inflation, in the sense that it's based on adding quantum physics to the story. So the ultimate source of the fluctuations is quantum fluctuations, but how they end up beside the horizon and what happens to them is different. So you need three ingredients in order to be able to generate density perturbations. The first is you need a cosmological background, which is going to allow you to perform the famous trick of taking quantum fluctuations, which are on subhorizon scales, and having them end up on superhorizon scales. So you need to have some way of doing it. Well, in general, if I have a cosmology which has a equation of state W, the scale factor goes like T to the 2 over T1 plus W, and the Hubble radius goes like T. So in the case of inflation, the way the cosmological background works in our favor is that we have W close to minus 1. So this exponent is extremely large. C is positive, the universe is expanding. So we have A going very fast compared to the Hubble radius. So the way we often describe that is the Hubble radius is nearly fixed, while the stretching of the universe is very fast, so that quantum fluctuations which are generated on subhorizon scales are quickly stretched to superhorizon scales. So that's the concept there. Now we switch, but that's not the only way of accomplishing the trick. The other way of accomplishing the trick is kind of in reverse, which is what we're going to be doing here. We're going to be using not inflation, but a kind of ecprotic contraction, where W is much greater than 1. So in the limit that W is much greater than 1, and we're contracting, that means T is shrinking towards 0 rather than growing, and W is much greater than 1. This exponent is very small, because it's nearly constant, while the Hubble radius is shrinking. So what that means is the universe is extremely slowly contracting, nearly fixed, while the Hubble constant is shrinking. So you begin with the Hubble radius is shrinking. So when you begin with the Hubble radius large, there are quantum fluctuations inside the horizon, and they just fluctuate, keeping their wavelength more or less fixed, while it's the horizon that shrinks around, through them. So at the end of the day, by the time you reach the crunch, you have lots of modes outside the horizon, but not because you stretched the modes, but because you shrunk the horizon. So this is the other logical possibility for accomplishing a cosmological background, which will accomplish the trick, taking modes that are initially inside the Hubble horizon and they end up outside of the horizon. So again, it has its own forceful logic to it, just like inflation does. Yeah? I don't think communication has anything to do with it. It has to do with solving dynamics of the. It's another effect of the Hubble of H in the equation of motion for the fluctuations is that when fluctuations go out, when their wavelength becomes large compared to the horizon, they become dynamically frozen. Okay, that's not a causal. We sometimes use the word causal communication maybe describing that, but it's really just a dynamic effect that comes out of solving the equations of motion. They were in causal contact. Okay, the second ingredient you need a source of scale-invariant fluctuations. You need the fluctuations to be scale-invariant. How are you going to do that? Well, that turns out not to be too hard at all. The way that's done in inflation is you take nearly massless fields and you put them in a de Sitter background. And that de Sitter background produces an effective potential in the equation of motion for a scalar field, which, in the perturbations for a scalar field, which ends up giving them scale-invariant fluctuations. So in that case, gravity was doing the work for you. But actually, you don't need gravity in order to make the scale-invariant fluctuation. You can just have to make sure that your action is scale-invariant, and it will produce scale-invariant fluctuations. So here's an example of a fluid which doesn't have gravity in it at all, okay, but which will produce scale-invariant fluctuations. Now, in the case that we're thinking of course, there is gravity, but the universe is contracting so slowly that gravity is negligible. Quite unlike the case of inflation. Inflation, you design it so that gravity is dominant. Here, the energy density is so low throughout this contraction process that gravity is negligible. So you can still produce scale-invariant fluctuations, and then just have the Hubble horizon shrink within them. So here's an example of such a theory, just with a negative exponential potential, which is sort of what I was describing as the eonotic part of the potential. You could either prove that they're scale-invariant by simply solving this equation of motion, but a more useful way of thinking about it is simply to notice that if I rescale the field and rescale the coordinates and equate this, okay, so I'm doing a scale transformation of the coordinates, the action just becomes a constant times itself. So this rescaling leaves the equations of motion unchanged. So this action is an example of scale-invariant action, and because it's scale-invariant, its solutions are going to be scale-invariant. You could either solve the equations of motion or immediately infer from this that the classical background solution for the scalar field is there has to be logarithmic in time, and that therefore delta phi, the fluctuations in phi, are going to have to be proportional to 1 upon t. And that proportionality constant, delta phi proportional to 1 upon t, that proportionality constant since phi has dimensions, it's 1 upon t, has to be dimensionless, and so that tells you that the fluctuations are scale-invariant. They have no finite scale associated with them. So a scalar field with an exponential potential is an example of a simple Lagrangian that will produce scale-invariant fluctuations. If that's the Lagrangian doing the vector phase, which is then described as the steep phase, then to leading order it will produce a scale-invariant spectrum. Notice, by the way, this is a non-gravitational mechanism. At this level of analysis, I left gravity out entirely. And this is unlike inflation. In inflation, the whole effect is gravitational. You take light fields, and with the de Sitter background, they obtain scale-invariant fluctuations. All light degrees of freedom in inflation obtain such scale-invariant fluctuations. The ones you want, like the inflaton, the ones you might feel neutral about, like the metric, ones you may not want to obtain scale-invariant fluctuations. Anything that's light enough will obtain scale-invariant fluctuations. It's a gravitational effect. It doesn't care about the details as long as the field is light enough. Here, this non-gravitational effect is selective. The only thing that's going to get scale-invariant fluctuations are potentials which have scale-invariant Lagrangians. So not all degrees of freedom get scale-invariant fluctuations, only the ones which have this property. And that is an interesting difference that we'll show up later. Of course, you have to include gravity. If you include gravity, it makes a small correction. It's not perfectly scale-invariant. That's how you get the deviation from scale invariance. Also, you don't want just a potential which is exponential all the way down, because that would lead to an energy density which is unbounded below. So there has to be some change in the shape of the potential, and when you include those effects in, you actually get a range of possible tilts, which are slightly shifted to compared to what you expect for inflation, sort of in the range of 0.97 to 1.1. slightly shifted to the blue, whereas inflation, the analogous statement for inflation is that the fluctuations would tend to be in the range of, I don't know, 0.94 to 0.98 or something like that. But they overlap quite a bit. And they're both consistent with the current data. Now, the third ingredient that you need, which we usually don't make a big deal about when we talk about inflation, is the converting of these scalar field fluctuations into density perturbations. In inflation, that turns out to be automatic, even if you just have a single scalar field. It automatically produces scale-invariant curvature perturbations. And that's related to the fact that in the expanding universe, a general potential perturbation can produce a combination of time delay and curvature perturbations, but it's the curvature perturbations which end up being the growing mode. So produce fluctuations in the scalar field, it produces fluctuations in both, but the growing mode perturbations are the curvature perturbations, and they end up being scale-invariant. In the contracting universe, the reverse is true. It's the time delay fluctuations that are the growing mode. So you don't automatically, just a single scalar field, say, in the picture I've described so far, produce, just from that, curvature perturbations. You need some way of mixing the time delay perturbations with the curvature perturbations, any degree, and then the scale-invariant fluctuations will be inherited by the curvature perturbations and you can go forward. But you need some mechanism for that to occur. And that was a big source of this confusion and discussion in the early years of the subject. But now I think that subject is pretty much under control. There are at least 3 different mechanisms that we're confident that work. The first of which, the first idea I think that was developed, actually was still built on the idea of describing the story of 2 colliding brains. And it has to do with the fact that as the 2 brains approach one another and they pick up speed, you can't simply describe the theory in terms of Einstein gravity plus a scalar field, but you have to include the fact that there are modifications to gravity as you approach the bounce. That idea led to a second idea. It turns out there's a second idea I'll describe in a moment, known as the entropic mechanism, which doesn't require extra dimensions at all. It just works fine in the usual 3 plus 1 dimensions, and it doesn't require extra dimensions or string theory. And then there's a third, more recent mechanism, which is called the adiabatic mechanism, which uses a different idea. So the colliding brain idea was that originally we were just thinking about the brains having one component to be associated with them, which was the modulus field associated with distance between the brains. And then we had this problem that when we had the wrong kind of, we had these time delay perturbations being generated, not the curvature ones. But when you expand that picture in a fuller way to include all the degrees of freedom in this picture, then it turns out mixing does occur as desired. Because the full theory doesn't just involve 1 extra dimension, but actually you begin an 11-dimensional theory, which includes a 6-dimensional Calabi-Yau manifold, which has various degrees of freedom, as well as the other bulk degrees of freedom in the story. And as the 2 brains approach, if there are fluctuations, say, in the modulus associated with the distance between the brains, those will inevitably produce fluctuations in other degrees of freedom, which, through some effort, one can show lead to this mixing effect. Now, a stripped-bound version of that picture is to just think about 2 degrees of freedom, the modulus associated with the distance between the brains, and the modulus field associated with the Calabi-Yau, the size of the Calabi-Yau body. So here I've drawn the picture as if there are 2 brains and only 1 extra spatial dimension. But in M theory, there's really each point in between actually contains, wrapped up in 6 extra dimensions, which is a Calabi-Yau manifold, which can expand and contract in volume or fluctuate in volume. So if we just keep that, even that 1 extra degree of freedom, along with the modulus field associated with the brains, we end up reducing to a effective 4-dimensional theory, which involves Einstein gravity plus 2 scalar fields. One linear combination parameterizing the distance between the brains, and another linear combination of the volume. So in that particular setup, what happens is we should really be describing not in terms of a 1-dimensional potential, but a 2-dimensional potential, in which the 1-dimensional potential I was drawing before represents that white dashed curve. But it's actually a curve along a more complicated surface. And as we know from examples in inflationary cosmology, that means that when we calculate the evolution of fluctuations, we can't just calculate the fluctuations along the potential, what I call the sigma, Those are the usual adiabatic fluctuations one gets in the analog of the adiabatic fluctuations one gets in inflation. But one also has to include the transverse fluctuations, which are the entropic fluctuations, which are called the entropic fluctuations. And actually both of those evolve. So what I just said before was that if I didn't have these entropic fluctuations, I only had these adiabatic fluctuations, what I end up with is essentially all time delay perturbations at the end and no significant curvature perturbations. If I include both degrees of freedom, I actually generate scale-invariant spectra in both of them because they share the same cosmic background. And now, what happens is that if we, what I've shown you over here is supposed to represent the plateau plus beginning to fall off the plateau. If this part of the trajectory represents, that represents this piece over here, that here we're continuing to fall down the plateau, etc. What one finds in the case of this colliding brane scenario is that there is a physical obstruction here, actually a negative singularity in the 5 dimensions, which prevents the fields from ever getting over here. So what inevitably happens is they approach this direction, they have to veer off. And the Big Bang occurs as the field went off to minus infinity. But what happens at this bend is that these transverse fluctuations, these fluctuations which were initially transverse, as you can imagine, now turn into longitudinal or sigma-like fluctuations. And this corresponds to a conversion, what's called a conversion of entropic fluctuations into adiabatic curvature fluctuations, so that the entropic fluctuations that were generated here are here converted after the exotic phase is over, are here converted to curvature fluctuations before the bounce, and now you've got the curvature fluctuations that you wanted. This provides the mixing for you automatically. Well, in the setting of string theory this occurs, it's a little hard to see that this is all going on. But once you learn the trick, you realize, well, I didn't need branes or extra dimensions, I just needed 2 fields in the contracting universe. And I could have done the same trick. So everything I've just shown you on this slide could just be done with 4 dimensions, with just choosing my scalar field of potentials appropriately. And a number of people, have really thought about that independently, because it turns out that this is very analogous to what one does in the case of curvature models, in the case of inflation, where there's a contribution from these involve 2 scalar fields, and each make a contribution to curvature perturbations. So at the end of the day, after taking some time to sort things out, it looks like that either this brane picture or this essentially curvaton-like 4D, effective 4D picture is not a problem to mix the scale-invariant fluctuations one produced into curvature perturbations and produce a scale-invariant spectrum consistent with what we observed. Yeah.
If you can represent the physics of inverters just using a purely 4-dimensional model, using this entropic mechanism, as you say, then the higher dimensionality of the original brane picture would not occur in your model. So if you can do it all 4-dimensionally, then you must not have been using the 5-dimensional protocol driver when you moved it.
Well,
that's just
yeah,
an effective field theory statement about solidity of effective field theories. If you can do a purely 4-dimensional,
so
5-dimensional theory, then it
as far as this mechanism, as far as this part of the story is concerned, we learned a lesson by beginning in higher dimensions. Then we discovered, actually, now that we understand what's going on, we didn't need higher dimensions. So yes, we didn't end up. It ends up
That's
you don't
a
need.
very important observation.
Yes.
It tells you that what you were using on a hydraulic theory wasn't really anything higher dimensional at all.
Not that it's part of the
It
story.
was a particular flavor of 4-dimensional effective theory that it gave you that enabled you to build those inverted models.
I agree. In fact, I think that's been sort of the lesson as we've been working our way all along, as though we were originally inspired by thinking about branes in higher dimensions. Almost the entire story, and maybe in the end, the entire story can be understood without it. It doesn't require it. So it might have just been inspiration and not required. We don't know yet.
That's an interesting question.
Yeah, it's an interesting question. I think the key open issue is the bounce. Whether or not one needs something like string theory to describe the bounce. And that's why this issue of singular versus non-singular bounces is important. And maybe I'll have a chance to say something about it, and maybe I won't. But that is why that's a key open issue.
So, can I ask another question?
Yeah.
So how about the question of initial conditions that
inflation has this property that you have quantitative vacuum as an factor, so whatever you start with is going to be wedged away. Can you say the same thing? I mean, you did say this about approaching the bounce, but it seems to me you expect when you come out of the bounce, the same thing that you had before would have re-emerged.
So by the time you reach the bounce, your fluctuations of interest are already way outside the horizon. So the usual physics, assuming that the curvature, that the metric just continues analytically through the bounce, means those curvature perturbations survive, but they're already outside the horizon. So they will just...
I'm just asking, what if you don't start from bunch Davis vacuum? Right?
So the bunch Davis wouldn't be at the bounce. The bunch Davis would be a question of going way back into the eonotic phase and saying, was it reasonable to assume that there was bunch Davis leading on? Okay, well, I guess I think the same argument for bunch Davis, at least in my mind, applies in both cases, which is if you assume that the universe has undergone enough inflation or enough explorasis that the universe is now totally dominated by the inflaton, or the field that has this large W, then what you're saying is that it looks like the theory looks like classically flat Einstein gravity with a homogeneous background, and that it should look locally on scales much smaller than the horizon, like the Minkowski universe, and therefore a bunch Davis vacuum.
It does have enough time to wash out the...
You have to have enough time, and the issue, so the same issue applies to both. And it looks like, because it's a super powerful mechanism, as indicated, that doesn't seem to be a hitch. So as much as one can make the argument for one, I think that argument passes for the other. The adiabatic mechanism, well, I'm just mentioning this because it's something that we're still working on at the moment, but also because it shows that actually, we're not done inventing that mechanism for producing scale-invariant fluctuations. This uses a different idea. This is the way we normally derive the spectrum of fluctuations when we just have a single field, not two fields. We have the curvature perturbation, which we can express in terms of the variable dk and z, where the dk that satisfies the Bessel equation, so we have one seen this kind of analysis before, and where z is a combination of the scale factor and some factor of W. And in the case of inflation, or in the case of ecpyrosis, one imagines that W is constant and that A has a certain behavior depending upon whether it's a de Sitter background or a contracting ecpyrotic background. Now the case for inflation, W is nearly constant and A in small time coordinates goes as 1 upon T. That ends up giving you the scale-invariant perturbations. For ecpyrosis, A doesn't go like 1 upon T. It's going like T to the 1 upon epsilon. Or T upon 1 of what I show you. T upon 2 over 3 times 1 plus W. But it has the wrong time behavior. And so for a single scalar field, you don't end up getting scale-invariant curvature perturbations. That's why you went through the full entropic mechanism, the two fields and all that. But suppose so it was claimed at one point in the theory that you could not make with a scalar field, a single scalar field, scale-invariant perturbations in a contracting universe for this reason. But it's not true. There is another trick. Another trick is the case here. We have a potential as a constant plus minus an exponential. So it goes from constant where W is close to minus 1 to very steep where W is much greater than 1. And the interesting behavior is a sort of transitional behavior where W goes from minus 1 to a very large value. And it turns out during that phase, 1 plus W goes as 1 upon T squared. And the scale factor is nearly constant during this phase because the universe is slowly contracting. So if you do that, 1 plus W is 1 upon T squared. That means this square root goes as 1 upon T. A is nearly constant. You get Z is going as 1 upon T, and sure enough, that gives you exactly the same result as inflation over that scale of modes. So that's just a demonstration of principle that there are several, you shouldn't think that we're locked into just one means of making these fluctuations. There are many means of making these fluctuations, probably more than we thought of so far. Okay, how can you test these models? Well, the nice thing about these models is there's easy ways to kill them. They make these two important predictions that are, I don't know how to wiggle from, so I think they are excellent tests. The first has to do with gravitational waves. In inflation, we know that the gravitational wave spectrum one gets is nearly scale invariant, and compared to what we're talking about here, has a large amplitude. For the ecborotic models, one ends up with this primordial spectrum, which in fact is exponentially small compared to inflation, and not scale invariant, in fact, light blue. And essentially this comes down to the fact that the behavior of the gravitational background is quite different. During inflation, h is nearly constant. And the amplitude of gravitational waves is proportional to h. So the amplitude of the gravitational waves is going to be constant as a function of wave number. It's nearly so.
Yeah. I hate to piggyback, but the isocurvature directions, which are then turned into the adiabatic, that is requiring a specific form for the potential associated with those fluctuations. And what I'm trying to say is that one expects that there might be a lot of those degrees of freedom that are transverse to the single
there'll be several modules.
And so obviously, well, not obviously, but presumably you don't want them all playing a role, so there must be something special about the one that turned into the adiabatic. Is there something special about one of them, or is it some sort of collective phenomenon of lots of them that is somehow building?
I haven't thought about the case where there are many. I would think there would be some particular combinations too that would dominate.
That's an interesting question, though.
Yeah, it is.
You might expect that there's a lot of degrees.
Yeah, no, I agree. But we haven't thought about it. Back to the gravitational waves. So the key difference between inflation and this scenario is that inflation h is nearly constant and large throughout inflation. During the ecborotic model, h begins small, where most of the fluctuation is very, very small and grows. And that's what's responsible for this different behavior of the gravitational waves. So that schematically, if you look at the dimensional strain of gravitational waves with frequency f as a function of frequency, for inflation, you begin with a spectrum which is scale invariant, but then as modes come in the horizon, they become more and more redshifted. So these are modes which are on the scale of the horizon. These are modes that have been on the horizon for a long time and become very redshifted. The dimensional strain, which was scale invariant outside the horizon, now has this famous slope to it. The cyclic model, on the other hand, has a spectrum which is extremely blue. So it actually begins with an amplitude which on the scale of CMB is exponentially suppressed because h is exponentially smaller during the contracting phase compared to h during the inflationary phase. And it grows, well, it's growing in amplitude, but then the modes redshift as they come inside the horizon, so it ends up with a spectrum which is more or less flat like this. So the point is that for measurements that we would see in the foreseeable future, well, here's what we have at the moment, but we're not yet sensitive enough to even see the inflationary ones, but it's clear that we're never going to get these primordial ones.
Since h is growing, you must have a way to do this. Why does it not?
You must have a, sorry.
Way to deal with non-energy conditions. Why does it not?
Well, you either, well, that's a question of the bounds, whether you...
Like you said, h is growing.
h is growing because you're contracting. So you either have to violate the non-energy condition, or A has to go to zero, or you have to some sort of enter the quantum gravity machine.
It's getting more and more negative. So it's negative first.
It's growing in negative.
Yes. You're contracting. Now, I should say there's a little bit more to this story than this because, I'm sorry, this is of course what one hopes to do with measurements of the classic microwave background. I hope I've drawn that to prove that scale and no one will take it too literally. But that's at least optimistically what one can hope to do. There's a little bit more to the story than this, which is, what I've shown you here is the primordial fluctuations due to inflation and the primordial fluctuations due to the cyclic model. There is another contribution which we normally ignore in inflation, which is crucial for cyclic, which is the second order effects. The fact that we have density fluctuations, which we're already observing, which come inside the horizon and undergo oscillations. They induce, or they produce, tensor fluctuations all by themselves, even if you had no primordial fluctuations at all. So there's a contribution, given the known density spectrum, assuming that it's the scale invariant, which is there, independent of the original source of those density Now, in the case of inflation, of course, they're down by several orders of magnitude compared to what inflation typically predicts, so they're negligible. For the case of the cyclic model, they are the dominant contribution. So inflation, and during the cyclic model, you'll never see these guys, but then again, you would never get to them when you get to these guys first. And although we don't expect to see them with the kinds of detectors we're imagining now, there are some people, Mr. Kiwara in the state Latham, but one does talk about probing down in this range, close to this range using DBO or futuristic detectors. And it's interesting to note that there is kind of a bottom of the search. There's a level, maybe this level, which just given the observed density fluctuations, with a few minor caveats, one should see fluctuations there in a model-independent way. And that would be the prediction for cyclic model. You see, that would be the only contribution you'd ever see.
So, Paul,
yeah.
I don't quite understand how you separate this from regular sources of gravitational waves like binary black holes, because they are higher order scalar induced.
Those are background to these, and you have to, or foreground, sorry, to these, and you do have to work hard to take them out. And so, well, now you're getting into what is going to be the tactics of trying to observe the cosmic source versus the foreground source. And
just my question is like, stars and galaxies, everything that we see are sourced by scalar fluctuation, and they produce gravitational waves.
That's right. And so they are here. I mean, so we hope that we'll see those in LISA and maybe LIGO or something like that. So you have to subtract out that foreground.
Not the DBO or follow structure. I can see people getting down to that, but the only other physical sources are, and very in the final year of being started with black hole neutron stars.
So the hope is, yes.
That's a small number of those sources. So like DBO plans to go to basically subtract out all of those, and then beyond that, no one thought of anything except for
people heard that in the back.
Sorry. So the claim is that the high frequencies where Paul has drawn the detector, that there, the physical sources that Nyash is mentioning are so few that you can detect them, track them out, and be left with just various possible stochastic backgrounds.
Okay, we continue to run. And I have no idea where we are in time.
We're pretty, this would be about your time.
Okay, well, let me...
I think the typical seminar can... how much do you have left?
I don't know. We're going to adjust it according to the center to your face from red.
What if we said about 5-ish minutes?
I'm going to go for 5-ish minutes. And other people ask questions. So the other effect that one can look for is the effect of non-gaussianity. And here the reason why, here one expects to see, whereas here the issue was that we don't expect to see gravitational waves, so we signal for cyclicity, if you like, is the absence of gravitational waves. Here the prediction is that you should see something that you wouldn't normally get in inflation, which is significant non-gaussianity. And the reason for that is quite simple, where in inflation, the idea is that you have a scalar field which is nearly massless, really flat potential, and it goes quantum fluctuations. If it were perfectly massless, it would have perfectly Gaussian fluctuations. With a slightly tilted spectra, with a tightly tilted potential, and have slight non-Gaussian contributions. But you can't tilt the spectra, you can't tilt the potential too much, you can't make it too non-Gaussian because the single scalar field, because you already have constraints on the tilt, which tell us that the potential can't be too different and flat. So given what we already know about the tilt, we know from the case of inflation the potential must be pretty close to flat, described by a single scalar field. For the case of the eonotic model, we have a very steep potential. So the case is opposite. You have a potential, you have a field which is strongly self-interacting, and so you expect it to be a large non-Gaussian contribution, which you cannot remove except with fine-tuning. So with inflation, you expect no significant non-Gaussian perturbations unless you add fields and fine-tuning. And the eonotic model, you expect that there will be non-Gaussian contributions unless you add fine-tuning. So that's kind of interesting. Since I only have 5 minutes, I will just roughly give you the idea of the picture it ends up being, the cyclic model. what you end up being able to show is that the expected value of non-gaussianity, which is typically measured in terms of FNL, is it's going to be of order 10s. The sign is indeterminate, so it could be, the pink here sort of represents the typical region plus, the here minus. But without fine-tuning, it's very hard to get several orders of magnitude of different terms. It's very hard to get a region which is close to 0. And that's to be contrasted with inflation, which predicts a value which is, for FNL, less than 1, unless you introduce exotic things to push it out of that range. Of course, once you introduce those exotic things for inflation, it predicts every possibility from plus 10,000 to minus 10,000 or more. So what I would say is that in the case of the CITA model, if one finds an FNL which is of order 10s, that's consistent with the picture. If one ends up measuring being able to push it down into the range of inflation, that's pushing the region. You have to fine-tune the model to do it. There's no natural reason why that should occur, and I believe that's a losing proposition. So, I'm sorry, because of the question I had to compress this a bit. We're varying over various parameters, degrees of freedom in this model, including the conversion mechanism. What is the duration of the conversion? The key parameter turns out to be when you convert from the entropic to the curvature perturbations. The key parameter turns out to be the duration of this conversion process, which is the greatest variation in the possible values of FNL. So we just wanted to show, to demonstrate for ourselves, as we push parameters in different directions, how far can we push FNL? So the pink represents sort of the sweeps region where it requires hardly any tuning parameters, no special tuning of parameters. As you tune parameters more and more, as you change the duration of inflation, you get some variation in the value of FNL. If you begin to push parameters begin to tune it by many orders of magnitude, you can begin to push FNL up or FNL down, but it's pretty hard to push it beyond this range. And empirically, a lot of this is excluded already. So here's sort of where we are at the moment. And so I think the key question is, do we end up somewhere over here, or do we end up somewhere over here? I think that will be a telling test. So the part of the talk I'm not going to get to is what are the potential advantages over inflation. But you might ask me about them. But let me just mention, I'll just say what I think the most important one is. I think the most important one has to do with the nature of eternal inflation. The problem of eternal inflation producing an infinite number of bubbles with an infinite number of possible physical properties inside. The idea that once inflation starts, unless you do something very bizarre, it will end up being eternal, and you'll end up with a universe in which if you span over the entire bubble universe, the sort of thing that Matt was talking about this morning, you'll end up with bubbles with every possible cosmological and physical properties. In fact, you'll end up with a situation where, as Luke puts it, anything that can happen will happen, and it will happen an infinite number of times. And the reason why it happens in eternal inflation is essentially because inflation is a very powerful mechanism in which the universe expands faster during inflation than it ever will in its later history. So that any rare fluctuations that keep the universe inflating and keep the eternity inflated will keep it going, keep it inflating forever, leaving room for quantum physics to make arbitrary things happen. And because of that, you lose control over the theory. It has no predictive power. It doesn't have all the kind of predictive power we assign to it, because in fact anything could have happened in such a universe. If you want to get around this problem, ask me how to do it. I'll stop there.
Let's just have one question, then we can get there. Are going to be cookies upstairs.
I just want to point out that if we keep right with that, we are also doing infinite number of adding groups to contradict this.
Yes, they're out there somewhere according to this theory. Yeah.
So let's
Okay.
So this is the same issue. you get your choice. You can have a B positive and a B negative. And so all things can happen. Then doesn't the B positive win? I mean, in other words, you get control inflation, and then there would be these pockets that would give you the bounce and stuff.
Sorry, I'm not sure I'm getting your question.
Well, what you
Are you getting-
you're making a special use of having an effective B which goes negative.
Yeah.
And there are other regions that might not be very high positive regions which are doing this incredible accelerated expansion. So wouldn't all of the arguments that people would give for this controlled inflation type of landscape apply, and these sorts of things would be small pockets in that, if you're using volume as a measure, creative volume.
I think it requires a longer discussion.
Okay.
We can do it.
Overview.
Yeah, overview. I think it's going to be a discussion.
Okay, so let's maybe the things that said is a time to come back for Jean-Louis' talk, shall we say at 5. That would make us only running half an hour behind, which is exactly where we started, so that means no slippage since like 9:30.